L'Hopital's rule allows us or gives us a shortcut in computing limits. Limit as x goes to a, or as x goes to plus or minus infinity. If for some reason you get a limit, you've got a rational function. If that limit has the form 0 over 0 or infinity over infinity, then we compute the limit as x goes to a of the ratio of the derivatives. This limit exists and is equal to L. And that limit's equal to L. We gotta make sure we check these forms. Some examples where those forms are really important. Bring me any candy today? You good enough for trick or treat? I always ask the little kids what their favorites are, and they'll tell me. My little princess said, "You got any peanut butter cups?" I ate them all. Oh, that's okay. Not if you're sitting on the sofa eating them all, I didn't. There's some understanding.
What's your favorite costume song?
This one little child comes as Frida Kahlo, you know, the unibrow artist. So I said, "Oh, aren't you cute? I bet you don't even know who you are." And she told me, "I'm the artist, Frida Kahlo." Here, take all my peanut butter cups. Oh, and this other little boy had this costume where it's like down here's the alien legs, and then behind him was an alien carrying him. And I thought that was more cool. Yeah. I was that mom who made the costume. Didn't want to make it. You know, I took a garbage bag and stuck it over their head. Tell me or something. Okay, so here's an example. Let's look at the limit. As x goes to 0 of x minus the sine of x divided by x times the tangent of x. So I need you to remember what the sine of 0 is and the tangent of 0. I'll give you a hint, it's round. So if I let x go to 0, this term goes to 0, sine of 0 is 0, and these are both 0. So I remind that I've checked that form, and now I'm allowed to use L'Hopital's rule. So I take the derivative of the top and divide it by the derivative of the bottom. This is not the quotient rule. This comes from using the equation of the tangent line. So the derivative of that x is 1. The derivative sine of x is the cosine of x. Down here, I've got a product of two terms, so we do need to do the product rule down there. So we've got the first times the derivative of the second, the tangent, secant squared. You want me to do everything, aren't you? Plus the second times the derivative of the first. Anybody know the cosine of 0? So my numerator is 0. That's going to make that term 0, the tangent of 0 is 0. So it has that form again. And the good thing about L'Hopital's rule is we can do it again. And get it out of indeterminate form. That Derivative of 1 is 0. Derivative of minus cosine of x is a positive sine of x. Here we've got a product rule. I need you to do this one. What's the derivative of secant squared of x? Close. Bring the power down. Raise it to 1 power less. Now you're in here to take the derivative of it. And you get a secant x tangent of x. And then we move over here and take the derivative of the tangent and get a secant squared. So let me simplify it a little bit so I can read it. Let's see, I've got a pair of secants multiplied here. So I'm going to get 2x secant squared of x times tangent of x plus another secant squared of x. And I know I don't have 0 over 0 because I see this term added on the very end. It's going to add a 1 down there. I don't think that stuff is going to add the negative 1, so I've got a non-zero over 0 form. So when x goes to 0, the sine of x is 0. That's 0, so that multiplies to 0. But this I said was going to be 1. 0 over 1 is not indeterminate. 0 over 1. So you can hang in there. You keep doing L'Hopital's rule until you get it out of the indeterminate form. All right, so here's one for you to try. Move the board over here in a minute when I write this down. The limit is x goes to pi over 2. And in the numerator, we've got the product of the sine of 2x with the cosine of x. And on the bottom, we've got x times the sine of 4x. Two times pi over 2 is pi. Sine of pi is 0. Cosine of pi over 2 is 0. Sine of 2 pi is 0. So you do have the right form. Let me let you take a minute and take the derivative of the top divided by the derivative of the bottom. Anything exciting happen on that first attempt through? Or is it still 0 over 0? Still 0 over 0. So let me make sure you get the right derivative. All right, so we got the first times the derivative of the second. The cosine is minus sine of x plus the second times the derivative first. The derivative sine of 2x is the cosine of 2x times 2. Downstairs, I got a product rule again. First times the derivative of the second, so I get a cosine of 4x times 4. And then the second times the derivative of the first. Nothing's really going to combine. I might just leave it there. I put pi halves in there. I get the sine of pi, which is 0. So all of that 0. Pi halves gives me 0 here. So my numerator is 0 plus 0. Let's see, 4 times pi halves is, what's 4 times pi halves? 2 pi? Cosine of 2 pi is not 0. Cosine of 2 pi is 1. So I get 4 times pi halves. So that's not 0, but this is 0. So we don't have 0 over 0 anymore. We have 0 plus 0 over something else. This is going to be pi halves. And this is going to be 4 times what I said it was, cosine of 2 pi is 1. I don't care about doing the multiplication because I get 0 on top and a non-zero on the bottom. And that one is 0 as well. Okay. Here's an example where L'Hopital's rule does not work well. The limit as x goes to infinity of 4x divided by the square root of x squared plus 1. Does anybody know what this one would be without using L'Hopital's rule? Techniques that we did in the previous section.
Would it be 0?
Not 0.
Oh, no, it would be. Wouldn't it be infinity?
Not infinity either. Looking at the ratio of the degrees, the highest power of x on top is x to the first. What about the bottom? That looks like an x to the first as well, doesn't it? So when the degree on top is the same as the degree on the bottom, you just take the ratio of the coefficients. So this limit should be 4 using the ratio of the coefficients. But let's pretend you didn't remember that and you attempted to use L'Hopital's rule. Let's look at what happens if you try L'Hopital's rule. It does have the form of infinity over infinity. So you take the derivative of the top and divide it by the derivative of the bottom. The derivative of the top is just 4. And at the bottom, think of that stuff as a quantity to the 1/2 power. Bring the 1/2 down, raise it to 1 power less, multiply by the derivative of what's inside. Now we're going to simplify. I can take the half out front and multiply with the 2, we'll get rid of that. Take the term with the negative power, move it on top of the positive power. So we've canceled here. And that's going to go upstairs with a positive power. So I have 4 times x squared plus 1 to the 1/2 divided by x. So you try this again. I've got an x on top, x on the bottom. It still has the infinity over infinity. We do it again. Bring this power down, times that 4, it gives me a 2. 1 power less, and it gives me a negative 1/2 power. The derivative inside gives me a 2x. The derivative downstairs is just 1. But since this has a negative power, we're going to put it down on the bottom, leaving us with 4x on top. And the square root of x squared plus 1 on the bottom. I've seen that somewhere before. We're stuck in a loop, right? So this process keeps us in an infinite loop. Without giving us any conclusion. So our conclusion is going to be, let's try to avoid using L'Hopital's rule when we've got radical signs like this, because it is always going to flip-flop back and forth because of the negative power from the derivative. And the derivative inside, I guess if this were first degree, we'd be okay. But the fact that we have a derivative inside is always leaving an x back in that position. So we'll have to always remember that we can still do things the way we did it back in section 4.3. Interpret this as being of the same power as that one. Okay, so there's your warning. Also, you got to make sure you check, does L'Hopital's rule even apply? L'Hopital's rule applies for 0 over 0 or infinity over infinity. There's a warning problem for that. X goes to infinity. X plus the sine of x divided by x plus the cosine of x. Oops, I want x minus cosine. X plus the sine of x over x cosine. I want you to explain why L'Hopital's rule doesn't apply. When it doesn't equal 0 over 0, y doesn't equal infinity over infinity. What's the limit as x goes to infinity of the sine of x? Sine of x, right? It doesn't have a limit as x goes to infinity. It's some number between 1 and -1. Same with the cosine, right? These two don't have limits as x goes to infinity. These limits do not exist because functions oscillate between 1 and -1. So I can't say that that limit doesn't exist. I'm just going to do something else. So I'll just do a little bit of algebra. Do the algebra, and then you're going to tell me what it is that I just did. Instead, write this like this. What did I just do? I just factored out an x. Right? Factored out an x. And I can, right? As long as I'm away from 0, and I'm pretty far from 0. Now that x cancels, and this limit does exist. These are just numbers between 1 and -1, but this grows large. So no matter where the sign is on its cycle, when you divide that number by infinity, that's going to go to 0. The same thing here. Cosine of x is some number between 1 and -1, and take any of those numbers and divide by infinity, and you're going to get 0. So now these two things go to 0 here, and I'm left with 1 plus 0 over 1 minus 0. And none of that involves L'Hopital's rule. What happens if you did try L'Hopital's rule? What would you get? Well, you said, well, this is in section 4 or 5, I'll do L'Hopital's rule. We said that that's equal to the limit as x goes to infinity of 1 plus the cosine of x over 1 minus the sine of x. And what? Still be something that doesn't exist, right? So you're still stuck with the problem of having these guys going between 1 and -1. You still have no idea what's going on. So be aware, be aware, be aware, be aware. Okay, let's look now at some other indeterminate forms. Here's a couple that we encountered back in chapter 2. We had 0 times infinity. And we had infinity minus infinity. So if you see any of those, we've got to do some other stuff before we can try to do L'Hopital's rule. So for instance, so I got all black. A minute, as x goes to 0, it's 0 from the right, x squared times the natural log of x. What was the behavior of logarithm near zero? Goes to negative infinity. So this term goes to minus infinity. And 0 squared goes to 0. So we do algebra stuff like this. We can do algebra stuff like this. Let's keep the logarithm here. So let's write that as 1 over x squared there. Dividing by 1 over x squared is the same as multiplying by x squared. So I can easily say that multiplying by x squared is the same as dividing by 1 over x squared. But writing it like this downstairs puts a 0 in the denominator, which makes this fraction go to infinity. And now I have infinity over infinity. So we can do L'Hopital's rule. Take the limit as x goes to 0. Here the natural log of x is 1 over x. We're taking the derivative of this as x to the negative 2. So you get negative 2x to the negative 3, or negative 2 over x cubed. And now we'll flip that over and multiply. And 1 over x times x cubed over negative 2. And one of those x's will cancel. And I get x squared over negative 2. Now we can take the limit as x goes to 0. And we'll get 0. Okay. Right, so that might work here. Try this limit. That'll look for those folks at home. Back it up, back it up. X times the sine of 1 over x. X is going to infinity, so I've got an infinity in this first factor. As x goes to infinity, 1 over x goes to 0. Sine of 0 is 0. So we have the exact same form that we had last time. Do the exact same steps. Let's see what you can get while I erase this board. Take that x that's in front, write it as a 1 over x in the denominator. And now it looks like 0 over 0, so we do a L'Hopital's rule from here. Simplify after you take that and write it. That's nice, isn't it? Top, right by the 0 at the bottom. you simplify before you attempt to take the limit. Here the sine is a cosine. Then we go inside and take the derivative. It's x to the -1. So you can get minus x to the -2, or -1/x². But you get that downstairs as well. So the simplifying part takes away the common factor. All you left with this limit. That limit going to give you, it's going to give you 1. Inside the parentheses, 1/x goes to 0. Cosine of 0 is 1. If you got that all the way through. There's another one for you. As x goes to pi over 2. I have to probably make it a one-sided limit because I've got a secant in here. Secant's not defined at pi over 2. So let's just go from the right. I don't care whether you get plus infinity or minus infinity. That doesn't matter. But as x goes to pi over 2, in here it looks like pi minus 5. So that's going to be 0. Secant of pi over 2 is 1/cosine of pi over 2. Cosine of pi over 2 is 0. So 1/0 becomes infinite. So we have 0 times infinity. But this time, instead of taking that polynomial term and putting it down here, we can use our trig ratios. Instead of moving that 2x minus pi and putting it on the bottom, why don't we just replace secant of x with 1/cosine of x? We're trying to get a fraction that has the form of 0/0, and I think that'll do it real quick. Secant is 1/cosine, so that just puts a cosine down here. Cosine of pi over 2 is 0. Numerator is 0. So I think this is much quicker. Top, 0, the bottom will be done. That's the form of 0/0. Derivatives real quick, right? Here the top is 2. Your cosine is minus the sine. Anybody know the sine of pi over 2? 2 over, that is a 2. That's a 1, so that's a -1. So when you have this form, take one of the terms and put it in the denominator, whether it's using a trig identity or just the old flip and multiply rule. Flipping the infinity minus infinity form. Let's look at the limit as x goes to 0. Of the cotangent of x minus 1/x. I'm sure all of your favorite trig functions are represented today. So to figure out the cotangent of 0, you need to figure out what the cotangent is in terms of sines and cosines. What is the cotangent in terms of sines and cosines? Cosine over sine. Cosine of 0 is 1, sine of 0 is 0. So that behaves like 1 over 0, which is infinite. And 1 over 0 here is infinite. So this has the infinity minus infinity form. And I'll go ahead and write it as cosine over sine so that you can see what it is. Okay. Dividing by 0, dividing by 0. All right, we did some of these back in chapter 2. And I said, just do the obvious. What's the obvious here? You do subtract. What do I have to do to subtract? I get a common denominator. I'm going to multiply this by x over x. And I'm going to multiply this by sine of x over sine of x. Common denominator. So I'm multiplying that by x over x. Multiply this by the sine of x over the sine of x. And so I'll put it as a single fraction. Now it has the right form for L'Hopital's rule. X times the cosine of x is going to become 0 when x goes to 0. Sine of x is 0. So now it has the right form. Now you can do L'Hopital's rule. The derivative at the top divided by the derivative at the bottom. See what happens. I need a couple of tries. Product rule here. First times the derivative of the second, plus the second times the derivative of the first. This sign is also a cosine. Upstairs with the product rules, first times the derivative of the second, plus the second times the derivative of the first. So those cosines on top add each other out. Let's go ahead and get rid of them. I'll try to take that limit. What do you find? 0 or 0. So do it again. 0 or 0 is the green light. I don't tell the rule again. Go back and forth. Oh. Well, put a pencil down, that means we're done. Let's try it. First, consider the second. Second, times the derivative of the first. Downstairs. First, times the derivative of the second. Plus the second, times the derivative of the first. And that sign is a cosine. I can see I got two ones added together down here. I'm not going to have 0 over 0. I've got a non-zero denominator. The numerator is 0. Because that one's going to 0, and that one's going to 0. I got 0 on top. That's 0. But that's plus 1, plus 1. That's not 0 over 0, that's 0 over 2. 0 over 2 is 0. So usually that's what it means. When we had radicals expression, we rationalized. Remember doing that kind of stuff? With these trig functions, you can get a common denominator and then put it in the form of 0 over 0. There are 3 exponential indeterminate forms that you need to be aware of. One to the infinity is not going to be 1. Sometimes it might, but not always. 0 to the 0. Well, an old rule that any number to the 0 is 1 is not true when the base is 0. And infinity to the 0. These are all indeterminate forms, which means you've got to do something to them in order to figure out what the limit is if you have any of those forms. What's the one that I did in class? We've encountered these in the middle of our problems in our Cal 2. So I had to see if my Cal 2 students remembered how to do these. Some of them did. So I'll talk to you next semester about this time. We'll do these again. Here's an example. Remember that one that I did in class because that was a pretty cool one. Oh well. Oh well. I just have to do my boring examples here. Let's look at the limit as x goes to 0. 1 plus 3x is in parentheses. 1 over 2x is the exponent. Limit as x goes to 0, 1 plus 3x raised to the 1 over 2x. Which of these 3 forms does this have? 1 to the infinity. The base is going to go to 1 when x goes to 0. Dividing by 0 gives a fraction that goes to infinity. This does have that form. We're trying to get this in the form of L'Hopital's rule that makes a fraction out of it. Either infinity over infinity or 0 over 0. So I'm going to use one of my tools that I have that takes exponents from here and brings them down. What function am I talking about? Logarithm, right? So I'm going to pretend I know the limit of this. Let's call it L so that I can make an equation. Now in this equation, I'm going to take the natural log of both sides. So a limit is a function that can be moved in and out of rules of functions. So I can put the logarithm in here, and I'll put the logarithm there. We'll have the limit as x goes to 0 of the natural log 1 plus 3x to the 1 over 2x. And that's equal to the natural log of L. And then I said the reason we did this was so that I can use that log property. It takes powers and pulls them down. The natural log of anything to a power is that power times the log of that base. And when I do that, the expression looks like this. If I leave it like that, then it looks like infinity times the natural log of 1, which is 0. So it has the infinity times 0. It doesn't give me my 0 over 0 or infinity over infinity. But I'll just do this to it. Put that 2x on the bottom. And now I have 0 over 0. So that's good news. We took it out from the indeterminate form of that type to the type that L'Hopital's rule works for us. We take the derivative of the top, divide by the derivative of the bottom. The bottom's just 2x, so its derivative is 2. Now I'm waiting on you to finish the derivative of the top. If this is the derivative of the top. But now I've only got an x right there. That x is going to 0. So this fraction on top becomes 3 over 1. I get 3 divided by 2. Remember, 3 divided by 2 is the natural log of L. Our goal was to find L. So how do I undo this step? Raise it to a power e. E to the 3/2 is our number L. Okay. That's pretty cool one, huh?
You said since it's at 3x, it's going to, you said 0?
Yeah, x is going to 0, so 3 times 0 is 0. 0 plus 1 is 1. 1 divided into 3 gives me 3. All right, so there another one. I do. I work the same way. Let's look at the limit as x goes to pi halves from the left. And on the base, I have 1 plus the cosine of x. And in the power, I'm going to have tangent of x. It has the exact same form, 1 to the infinity. Convince yourself of that. Cosine of pi halves is 0, so the base goes to 1. Tangent is sine over cosine. Sine at pi halves is 1, cosine at pi halves is 0. 1 divided by 0 is infinity. So we're going to use this same sequence of steps. Call that L, take the natural log of both sides, and bring the power down. Then we're going to try to put it in one of our forms for L'Hopital's rule. Yes. Natural logarithm in there. And bring the power down in front. Way back over here. I'll be down here and then move my camera. The tangent of pi over 2 was infinity, wasn't it? Because it's sine over cosine. Cosine of pi over 2 is 0. So this behaves like infinity. Cosine of pi over 2 is 0, so this behaves like the natural log of 1. The natural log of 1 is 0. So it's got that indeterminate form of infinity times 0. Gotta make a fraction out of this somehow. The quickest way to do that is replace tangent. Tangent is sine over cosine. So I've got the sine of x, there's the cosine of x, and then let's put the logarithm up here. Sine of pi over 2 is 1. Cosine of pi over 2 is 0. 1 times the natural log of 1 is 0. Cosine of pi over 2 is 0. So it's got the right form now. Use L'Hopital's rule. So guess which term I'm going to take the derivative of? I'll wait for you slow folks to take the derivative of the top. A little product rule action up there. Something you like? First times the derivative of the second. So let's see, it's a logarithm, so that goes here. And the derivative cosine is going to give me a minus sign there. And then the other way, I didn't leave enough room, so I got to scooch that out of the way. Got the second times the derivative first. Oh. I don't have to simplify it. I take the limit. X is going to pi over 2. Sine of pi over 2 is 1. That's going to give me a minus 1. Cosine of pi over 2 is 0. My numerator is not going to be 0. Cosine of pi over 2 is 0. Log of 1 is 0. Cosine of pi over 2 is 0. Sine of pi over 2 down there on the bottom is going to be 1. So I got a minus sign. So it's a minus 1. So the top simplifies to -1, the bottom simplifies to -1. -1 over -1 is just 1. So the natural log of our limit is 1. We do this peel off the logarithm again. Erased it. Peel off the logarithm with an exponential function. Even 1 is our limit. Both of those look like that. One of these right quick. As x goes to 0, of x raised to the sine of x. So the base and the exponent are both 0. Zero to the 0 form, follow the same sequence of steps. Our goal is to get that exponent down in front, then we can see if we can write it as a fraction of the form 0 over 0 or infinity over infinity. So let's start by calling that expression L, take the natural log of both sides. If anything good happens. Expression. Pull that power down in front. I don't have a fraction, so I don't think I have any 0 over 0 stuff going on yet. The natural log of 0 is infinite, sine of 0 is 0. So this has the form of 0 times infinity. What would you like to do to that? Let's take this down and put the denominator as 1 over the sine. You can leave it there because it has a form of infinity over infinity and do the L'Hopital's rule, or you can replace the sine or 1 over sine with that cosecant. You have a preference which way you do it? Let's leave it here. Derivative of log of x, right? I got 0. Now I got infinity over infinity. And here at the top is 1 over x. Derivative of 1 over sine of x.
So if you're not changing to the inverse identity, then you have to keep it the original fraction, like 1 over sine of x. Meaning, like, if it was cosecant of x, then you could just put sine of x in the bottom without 1 over sine.
All right, well, you
Right.
can put a cosecant here if you remember how to take the derivative of cosecant. But then when you try to evaluate cosecant at points, you have to think in terms of sine. So I just thought it'd be just as easy to leave it here. Right? Here's the bottom, times the derivative of the top, minus the top, times the derivative of the bottom, all over the bottom squared. Natural log of L following us around to remind us at the end. So I'm going to simplify this. This is 1 over x here. This is a minus cosine of x over sine squared of x. Let's do the flip and multiply step. And flip and multiply step. Got all this stuff here. One over x, this flipped over will look like a sine squared of x over a negative cosine of x. Make a single fraction out of that. Sine goes to 0, x goes to 0, cosine goes to 1. 0 over 0 times 1 is 0 over 0. So yay, we can do it again. Now, use the power rule to take the derivative of sine squared. Bring the power down, raise it to 1 power less, multiply by the derivative of what's inside. Bring the 2 down, raise that to 1 power less. The derivative of the inside gives me a cosine. Downstairs, we've got a product rule. So it's the first times the derivative of the second. The derivative of cosine is minus sine, so I'm going to take those 2 minuses and make a plus. And then the other way, derivative of minus x is minus 1 times the cosine of x. But I think we're done with our L'Hopital's rule, because look, here's a 1 on the bottom. That's 0. So my whole numerator is 0. That's 0. That was 1. So let's see, I got 0 on the left, natural log of L on the right. We want L. L is e to the 0. So L is 1. So we've done a 0 to the 0. We did 1 to the infinity. I think now we need something that looks like infinity to the 0. We'll try one of those. That one? If I never did class. So do all the examples and make them up. You're not acting like it, but this is some of the coolest stuff you'll ever learn. You should be really enthusiastic right now. Forgot what form did I say I was looking for? Infinity to the 0. Let me think what becomes infinite here. Okay. So do you think that looks like infinity to the 0? The natural log of x to the 1 over x as x goes to infinity. Logarithm's a growing function, so as x goes to infinity, so does the logarithm. 1 over infinity goes to 0. So same bunch of steps. Call it L. Take the natural log of both sides. See if we can make a fraction out of the left-hand side. That 1 over x comes down in front. Remember, our goal was to make a fraction out of this, so let's take the 1 over x from in front. Let's just do the multiplication, which gives me an x on the bottom. Right, multiply by 1 over x, multiply the logarithms here, and then the x goes on the bottom. Funny looking numerator, that's not a product. That's the natural log of the natural log of x. But as x goes to infinity, I get something that gets infinitely large. Natural log continues to grow. So my numerator is infinity and my denominator is infinity. So we can do the L'Hopital's rule. There you go. Log of u. Root log of u is 1 over u times u prime. It's the old days when I would just get chalk all over myself. So the derivative of the log of x is right? Because 1 over u gives me 1 over log of x, and then the derivative inside is a 1 over x. So we can put them together. Or we can even put it like this. I'm dividing by 1, I don't need the 1. So what's the limit on the left-hand side going to be? 0. All the x's are on the bottom. And we exponentiate both sides. So 1 is equal to L. Zero over 0, infinity over infinity. Knock out L'Hopital's rule to make it a limit. 0 times infinity, infinity minus infinity. Do some algebra to make a fraction of the right form. Exponential indeterminate form, 1 to the infinity, infinity to 0, 0 to the infinity. Use a logarithm. So I told you how to do it. Now just go home and do it. That's all I want to say about that. Okay, next time we're going to be doing max and min problems, finding the maximum and minimum of functions. And you think, oh, I've already done that. We're going to do it with word problems. So I've got a handout of examples. Steps, you know the steps to find the max and min. Take your function, take its derivative, set equals 0, do the first or second derivative test. The only difference is you got to come up with the function.
So this is like the related rates.
It's like related rates. You got to find a function that you're going to take a derivative of. So get fired up for that on Wednesday.
Everyone's fired up for that.
Everyone is, I can tell. Always hard to contain your excitement in here.
You said when it's 0 times infinity, turn into a fraction.
Turn it into a fraction. What do we do here? We took one term and put it on the bottom, right? Put its
Right.
reciprocal on the bottom.
Right.
Or if you have a trig function, you can do a trig identity.